Welcome to the PLAXIS Elite training session on material volume meshes. In this session, we will talk about the challenges related to layered models, the use of material volume meshes to create models of additional complexity, and then look at the application to a specific tailings dam or open pit. A traditional geological conceptual model is built up using non-intersecting layers. This is also referred to as a layer cake model. Such layer cake model was supported in PLAXIS LE paradigm under the following restrictions. Regions must have vertical boundaries. Surfaces must not fold over themselves. Each block of material must have an associated surface, and surfaces must not create negative volume layers, or, in other words, they must not cross through each other. In reality, there are situations that cannot be modeled with a layer cake paradigm. Applications which are challenging to model with a layered approach include situations with folding geology, complex construction scenarios, open pits, or bodies which may be very non-layered in their representation, as well as any application involving near vertical contacts between adjacent material zones. A new material paradigm was needed to handle these unusual situations. Material volume meshes were introduced into the software as a method for overcoming the limitations of a layer cake model. A material volume meshes is a 3D object that defines a volume of material that overrides the materials defined by existing region and surface blocks. It is important to recognize that material volume meshes distinct and separate objects from the regions and surface paradigm. Therefore, they are useful for modeling obtuse volumes of materials that are difficult to represent with regions and surfaces. Each material volume mesh represents a separate and distinct volume of material and can be assigned a constituent of model unique to that mesh. Material volume meshes are automatically clipped internally by the solver if they fall outside the lateral extents or the uppermost surface of the module volume. Therefore, they will be clipped at the uppermost topology. Visually, material volume meshes may display outside the module volume, but these outside artifacts are not included in computation. The order in which material volume meshes are organized is significant in relation to priority. Material volume meshes that are entered farther down on the list will override the ones above. A material volume mesh must also be an enclosed mesh without any holes. The other side notes regarding material volume meshes are that the side walls joining top and bottom parts of the mesh can be excluded if the side walls are perfectly vertical or if the side walls lie outside to the horizontal extents of the module volume. In order to add material volume meshes to a model, they can be added under the meshes objects as MVMs, are always meshes. Within the PLAXIS LE slope stability software, there is a separate manager dialog to manage the MVMs. The display of the MVMs as well as their order of priority can be adjusted in the manager dialog. In order to add a material volume mesh to a PLAXIS LE model, the mesh must be copied from PLAXIS Designer and pasted into the material volume mesh dialog in PLAXIS LE. The material property can then be assigned in PLAXIS LE. This example shows an example analysis of a tailings dam with stability analysis performed by BGC. The slope and geology required a 3D model to properly analyze. The core is twisted like a ribbon and represents an impossibility to model with a layered cake approach. An example of how this technology can be utilized may be illustrated with the construction of a tailings dam model. In this real-world example, the geology was represented with 5 lithology units, of which each had their own shear strength. There is no lensing nor pinching out between the layers, and therefore the model could be utilized a layered cake approach with these surfaces. The surfaces are shown exploded vertically out of the model in the figure. The core of the Earth then transitioned between an inclined core and a central core. Each of these representations required different layer representation. In other words, it was impossible to represent both an inclined core and a central core with a surface and layer approach. A material volume astral object could be successfully used to represent the entire core. This animation shows the completed analysis utilizing material volume meshes in order to represent the complex combination of central and upstream alignment of the dam core. The spatial analysis feature allows the stability to be analyzed at a number of different locations across the earth dam structure in 3 dimensions. The resulting critical slip surface geometry can be seen. The color of the columns related to the material that is sheared through at the base of each column. Therefore, it can be seen that the material sheared through represent a very irregular and 3D pattern. Another example of material volume meshes application is the analysis of an open pit slope stability. Open pits are often located in zones where the geology may be highly three-dimensional in nature. Ore bodies may be extruded based on historical volcanic activities rather than laid down in a sedimentary fashion. Therefore, the representation of some geological objects is better suited to material volume meshes. The benefits of applying material volume meshes to this application are that a more accurate representation of the factor of safety can be computed in a 3D fashion. The Jew strata is represented more accurately and therefore improves the alignment of the numerical model with the reality. Thank you for your attention.